all here today for the real-time fault level monitoring lunch and learn. So this is a project that has been facilitated by the Energy Innovation Centre, and we have representatives today from SP Energy Networks, UK Power Networks, and Outram Research. So you're going to hear from Adam from UKPN, from Ralph from SPEN, and from John and Kate from Outram. They will take you through the history of the project and kind of the main findings that we've come across over the past few years. I'm sure there's going to be plenty of questions, so we will endeavour to give as much time at the end of this session for them. So if we can keep them towards the end of the slide deck, which will hopefully be done in 35 to 40 minutes. So thank you very much for your time today. My name's Ed from the EIC, by the way. This is what the today's session is going to entail. So we'll take you, like I said, through the context and the background of this project, kind of an overview and an introduction of why real-time fault level monitoring matters, and an introduction into the technology that is being developed and implemented. We will look at a bit of the independent testing and validation that has gone on, and then move into this real-world deployment of the RTFLM and benefits for use of this technology from the view of the two networks that are involved here. So I will hand over to Ralph to give a bit of the context and the background of this project and where we've been over the past few years.
Thanks, Ed, and good afternoon, everyone, and welcome to this webinar. Thank you for joining. Good to see some familiar faces on the call and some new faces as well. So I'm Ralph Airwalker. I work for SP Energy Networks, and I've been leading this project on behalf of SPED for the last 5 or 6 years or so. So just to start with, I think it's important just to make sure everyone's got a common understanding of what we mean when we talk about network fault level. So fault level is the electrical term that we use to describe the expected short circuit current that will flow through a network in the event of a fault. So it's got nothing to do with how many faults we experience on the network. It's all about what happens within the network when we actually get a fault. So to give an example of a fault that we could experience, so if you imagine a tree falling onto an overhead line conductor, that tree will create a low impedance path between the high voltage conductor and ground, and all the energy that's within the network at that point in time will rush towards that fault location, and that is the fault current flowing through the network. What happens next is our network protection devices will see that fault current, and they will signal the relevant circuit breakers to open to de-energize that circuit and make the circuit safe. But for that short space of time in between the fault occurring and the network protection systems operating, the network itself needs to be able to cope with that big surge of energy, that fault current flowing through the network. And that fault current is much, much higher than normal operating current. So the switchgear and other plants on our network, so transformers, circuit breakers, cables, cable joints, and so on, all need to be rated to withstand a maximum fault level value. And as we connect more and more connections to the network, particularly distributed generation, that's pushing up network fault level. So as a result, that it's fault level that often limits the capacity of the network for new connections. And the difficult thing about being able to measure fault level is that we're trying to measure essentially something that's not always there. Fault current is only normally there in the event of a fault. We can't go through around the network throwing faults just to see what the fault current is. So we've had to approach this using some fairly innovative approaches. And in fact, when we very first started the project, even predating my time with the project, when it first started, it was actually seen as something that was potentially impossible to do. But through as we'll go through this presentation, you'll see how we've been able to achieve it. If we just move to the next slide, please. So just to carry on with follow up on the last slide, so distributed generation will continue to accelerate on our network as decarbonisation and decentralisation to facilitate the net zero transition and the green industrial revolution continues. Managing fault level was always and is already one of the greatest network planning and operational challenges that we face. And currently and historically, we've managed that through network modeling calculations. So we have lots of offline models of the network where we model all the different assets that are connected to the network, or the generators, or the customers, the load, and through those models we calculate what the fault level is for a given area of the network. But those models are only as good as the quality of the input data, and have to rely on some assumptions in terms of things like feed from the transmission networks, and they're also getting more and more complex as generation technology advances as well, and different technologies are being connected and deployed across the network. So in response to this, Scottish Power initially and at the Stage 2 project, UK Power Networks have joined the project, and we've partnered with Outram Research to develop a real-time fault level monitor to see if we can capture fault level through real network measurements as close to real time as possible. So the approach to this in terms of the innovation project is we had a Stage 1 project, which was to develop and test a prototype as a proof of concept on the network. That project was successful, and we were able to capture fault level measurements. But some questions came out of that in terms of the learnings. So it was the first time it had ever been done. So questions were asked around, well, if we get, if the measurement is different to what the models are telling us, how do we know which one is correct? So how do we validate those results? And also, of course, we recognize that we can't just go around installing prototype devices all over the network. So we needed to continue the development of the device to make it more robust and redesign it to be a fully deployable solution as business as usual. So that was the idea when I set up the Stage 2 project, and what we'll take through during the course of this webinar is the learnings that we've captured as part of this project. So firstly, the work we did to prove the measurement fidelity, so some independent testing and verification that we've done to prove that. We've then redesigned the device to take it from prototype to a operationally deployable solution. We've completed our first operational deployments, and in total, SPED has deployed fault level monitors during the course of the project at 9 or 10 different substation sites now, capturing fault level measurements from 6.3 kV up to 33 kV distribution voltages. So during the course of this, we'll be developing the commissioning process and design, and we're now looking to deploy as business as usual during the course of the rest of RIIO-ED2. And I think I now hand over to Adam Mackey from UK Power Networks, just to continue with some context and background.
Good afternoon, everyone. My name is Adham Mackey. I've been leading on this innovation project for the past 2.5 years. I'm pleased to be here. Good to see so many familiar faces as well, and I hope everybody can get something from this presentation. To set the context for UKPN joining this consortium, Stage 2 offered a clear route to validate fault level models using the real-time data from the network, not in the lab or under ideal conditions, but across the distribution network with real operating constraints. Our role within the consortium was threefold. We firstly acted as delivery and trial partner, hosting installation in our network. We also provided a complex real-world operating environment across multiple voltage levels. And thirdly, we contributed to the technical validation and learning, helping us to bridge the gap between what has been achieved in stage 1, and that is the prototype, to something that is operationally credible. So in practical terms, UKPN has installed and trialed 6 RTFLM devices across 6 substations. And given the nature of the innovation project, or the challenge, sorry, that we're trying to tackle, we saw the value in expanding the evidence base beyond a single DNO. And that was also a reasoning for us joining this consortium and investing in this project heavily. The sites were chosen to reflect very different challenges, from 11 kV network with aging switchgear and high distributed generation density, through 33 kV meshed primary substations, and up to 132 kV, where transformer paralleling and GSP fault level limits become critical. From a technical perspective, we validated RTFLM outputs against our computational models. And crucially, that validation happened in real operating conditions, as Ralph mentioned earlier, including live switching outages and network reconfiguration. We also supported the off-network testing through the lab test conducted at an early stage, and the oversea testing using a network-fed fault, which the team will share more information about throughout this presentation. And this is all to stress the network-fed faults, is to stress the device beyond the normal operation. And all of these steps or attempts that we took are to fed directly into assessing the readiness for a business as usual environment of such device. And for UKPN, the value is very practical. It's improved confidence in switching decisions, post-fault restoration, and outage planning. And in the longer term, it supports better utilization of existing assets, potential deferrals, faster, lower cost distributed energy resources connection. In short, this stage showed that real-time fault level measurement can move from a prototype to operationally credible technology. Move to the next slide. So why did we bother? Or why did we invest in this? As I mentioned earlier, and Ralph as well, the real-time monitoring of the fault level across multiple voltage levels offers some very real safety, operational, financial, and strategic benefits. And this slide is basically all about the value proposition, or the significance of having that real-time visibility. I'm going to dwell in this slide for a couple of minutes, partly because it brings all the key use cases in one place, and partly because it's a chance to grab a screenshot, maybe for something I learned today, LinkedIn post. So I've organized this slide into 4 pillars. Aware of the audience we have from different backgrounds and teams, and different use cases will resonate with people differently. So starting at the first pillar or dimension, this is basically the foundation. Everything else built on this. So at the most fundamental level, this is all about safety and risk management. All our assets, whether it's switch gears, cables, transformers, and bus bars, have a hard time fault level limits. And when these limits are exceeded, the consequences are immediate. So what the real-time fault level monitoring gives us is the ability to see risks developing early before something fails. That means preventing catastrophic damages and operating the assets within the design limits, as well as not operating blind. It helps us maintain the protection settings of the relays appropriate as the network change, and reducing mistrips and unnecessary outages. Operationally, however, fault level changes every time the network is reconfigured. during switching, restoration, or normal system running, real-time monitoring allows the control room operators to see the fault impact before switching, which means avoiding unsafe configuration and enabling safe energization even in close onto fault situations. And when the fault occurs, that same data is already captured. So it gives us an accurate pre-fault and during fault records to support better root cause analysis and reporting. Now, stepping into the planning and strategy view, traditionally, fault level studies are snapshots. They tell us what might happen, but with real-time monitoring, we turn this into a continuous picture of what actually happens on the network. It allows planning models to be checked against real network behavior and highlights where fault headroom is being eroded over time. And this basically means that reinforcement is targeted only when it's needed. At the same time, it gives us some auditable evidence for compliance, supporting our reporting and confidence in our long-term investment decisions. And finally, for our system operators, this is where the efficiency and low carbon energy transition come together. One of the most common responses to high fault levels is network splitting, and that process is quite expensive. With real-time fault level monitor, we are able to see the contribution of DARs and track it. We can also operate the network in parallel configuration for a longer period with confidence and only split the network when it's required. And in regards to the DAR connections, this helps us also manage the bidirectional flow and make better informed decisions when it comes to connection. So the ultimate value is flexibility without the unnecessary cost, supporting more efficient low carbon networks. And we move to the next slide, please. So to close this out, at its core, it's a shift from static worst case planning to a dynamic evidence-based operation. I just want to stress here that we're not removing or jeopardizing safety. We're rather replacing the guesswork with evidence. In other words, moving from a fixed worst case limits to a dynamic constraint based on live condition and clearly defined threshold. And how does that work for us? It's essentially a closed loop cycle. It starts by sensing, capturing this data from the network. We then analyze that data, turning it into an insight, spotting patterns, trends, and anomalies. Next, we move to validation, which allows us to check our planning models and protection settings against the measured reality. Ultimately, that gives us the confidence to decide whether it's a planning decision, a connection choice, or an operational action. And we finally operate, switch, constraining, or configuring the network safely and with justification. And the loop carries on. And what that means, it moves us from the uncertainty band to the measured reality, from the assumed headroom and to the real headroom, creating operational freedom ultimately, and allowing us to connect more generation, defer unnecessary enforcements, and protect our aging assets. And I shall pass back to John for the next slide. Thank you.
I think it's me, actually. It's back to me.
Sorry, Ralph. Yeah, it's Ralph.
So thanks for that, Adam. So next, let's introduce what the real-time fault level monitor actually is and what it looks like, how we connect it up, and how it operates. So you can see on the photograph on the right-hand side of the slide there is what one of our devices looks like within one of our primary substations. So to give an idea of scale, it's a similar sort of size to a standing fridge freezer, or for more technically minded people, a 19-inch comms rack, or just to the left of the photo, you can see it's situated next to a 500 kVA distribution transformer. And the device itself is modular in the way it's constructed. So there's three bottom racks or trays, and they have banks of low voltage inductors in them. And then the next tray up contains the power electronic switches and protection devices. And then the two trays above that contain the main processor unit and the comms rack as well for interfacing with our SCADA to allow us to take the real-time measurements through to our SCADA system, so our control engineers have access to it in the control room. The way we connect these up is, firstly, we need to connect the bank of inductors to an LV distribution supply or LV distribution board that has to be fed directly from the same target bus bar that we're looking to measure fault level at. So in that example there, the distribution transformer next to the RTFLM steps the voltage down from 6.3 kV down to LV, and there's cables out the back of the RTFLM that run alongside and connect to that LV distribution board. We then take a voltage measurement for the voltage transformer on the target bus bar, so which could, whatever that is, 6.3, 11 or 33 kV and so on. And the device, when it's switched on, will then switch the LV inductors, the LV inductive load, multiple times a second using the power electronic switches. What that does is creates a fairly sizable voltage response at LV, which, just to note, if the LV distribution board is also supplying customers, there's things we can do to configure it to make sure that we stay well within P28 flicker limits. But it creates a reasonable voltage response at LV, which can then be seen as a very, very small voltage response at the higher voltage via the VT. Because the device is switching the inductive load itself, it knows precisely what time and where to look on that voltage waveform, so is able to see those very small voltage responses. It also has built-in CTs, so it's got the change in voltage and the change in current. It can then use that relationship to calculate the network impedances at that part of the network, and from that it's able to calculate the fault level. So it's capturing fault level through real network measurements and observations. In terms of the KPIs that we set for this project, our initial targets were to be able to measure fault level to within a 5% threshold and identify a 10% step change in fault level within 15 seconds. So what we mean by that is normally fault level is around the same value for a given network topology, but if we switch the network and change network topology, that can result in a step change in the fault level, and we need to be able to identify that quickly as well, which is more complex than it sounds, because we're also capturing multiple measurements and making sure that we filter out noise. We have to identify between real step changes and other things that are happening in the voltage waveforms. But in terms of peak performance, what we've been able to demonstrate is that we've been able to measure to within a 1% threshold in terms of the fault level and identify a step change within 4 seconds. So our approach to the project has been to prove the technology, develop from a prototype, and then deploy as business as usual, as I said before. So for the next part, I'll hand over to John Outram from Outram Research, who will take us through the independent testing we've done at test facilities to demonstrate the algorithm fidelity.
Okay, everybody, I'm John Outram, and we've been the developers with Sven and UKPN of this product. Well, so far, the comparison of RTFLM results with models has generally, but not always, been quite good, particularly if the model has been carefully constructed. But in some cases, the model input data has been not just a bit wrong, but grossly wrong. So there's also been a certain amount of skepticism as to whether we could actually do the job in the first place. But ideally, we want to test more simply, more directly, and avoid any remote dependence on conventional models with their need for perfect input data. And just remind ourselves, we're looking for better than 5%. So how can we do this? How can we test this? we thought we could tackle this using two complementary methods. Method one would attempt to validate the algorithm in a variety of scenarios, and for method two, we'd take a complete unit to a site where we could do full system tests, actually put real faults onto a real network at real operational voltages to demonstrate that we could predict what the fault level currents would actually be. Method one could be performed on a real-time digital simulator. Put that slide up, please, Ed. With what is called hardware in the loop. Can we change the slide, Ed? Thank you. And we could do that at the PNDC, the Power Networks Demonstration Center in Cumbernauld. And in this test environment, a computer is used to model a network, and the hardware under test, in this case the RTFLM processor, is merged in with the computer. And this is modeling by computer with what's called hardware in the loop. And here's how it works. A network model, in this case a section of Spen's distribution network in Liverpool, is loaded into the simulator prior to the tests. Our model contained 132 kV grid supply points, multiple 33 and 11 kV interconnected substation features, and ran down to LV. The network can be simulated entirely on the RTDS, and bolted faults can be applied and current examined at any chosen node, so we can actually obtain fault level results for both peak make and RMS break, the two key parameters, very easily. The computer can also model the high voltage, high current section of the RTFLM, all that's within the red line on the diagram, all the area within the red line. And that just leaves outside the red line the measurement processing unit, the RTFLM processor. And that's the real bit of hardware, the bit that's included in the loop. The processor behaves exactly as it does in the full hardware system, and it doesn't know that it's being talked to or being replied to by a computer. It thinks it's in a network. The processor initiates disturbances as normal, and that physically stimulates the computer. Then the computer models the disturbance generation hardware to synthesize the pulses at LV. It models the coupling through the transformer to the target bus and the voltage response to them. Those digital responses are then fed to digital to analog converters to provide the physical response signals back again to be measured by the processor. So the processor has the same information as it has in a full system, and it computes the prospective fault level as normal. So, whereas previous model validations compared RTFLM results which are derived entirely from hardware measurement with models derived entirely from lists of parameters and hopefully accurate lists, in this situation, the RTDS situation, any errors or omissions in the input data, for instance, incorrect cable length, would affect not only the calculated fault level, but also the network response to stimulation. So that means we can compare like with like. The RTFLM result will be affected just as the modeled fault level is, so the comparison is now much less dependent on the quality of the input data. The real-time digital simulator is a very good place to start, really, because it's got some major plus points. It's safe, there's no high voltage involved, there's no physical risk, we don't need outages. It's flexible. We can change things around. We can test at different voltages. We can change the characteristics of the disturbances, and it's repeatable. But while the computer can consistently generate accurate digital data, there's still some error sources we need to be aware of. It's a sampled system, which inevitably means there's a processing latency, and that's the time it takes the computer to recompute the set of results for each sample. It has limited analog output resolution, and that's a challenge if we're looking for very small voltage variations, which we are. And while it tests the processor function and the algorithm, it doesn't test any of the high current hardware involved in disturbance generation. There's no typical noise arising from normal network activity, no vagaries arising from parasitic network effects or imperfect hardware. Next slide, please, Ed. Here's a picture of the real-time digital simulator and us looking at screens, looking for test results. We did some 59 tests at the PNDC. We tested both 11 and 33 kV bus voltages under different conditions. We changed the input frequency. We confirmed the effect of interconnections.
think John might have dropped off there.
Must be some connection.
Want me to jump in?
Yeah, I was just going to say, Ralph, if you could.
Is John back?
No, I don't think so.
So I think what John was going to continue to say there is with the flexibility of the real-time digital simulator as a control substitute for the network allows us to quite easily assess multiple network topologies, multiple scenarios over quite a short space of time. So they completed 59 measurements over the course of 7 days. And it really did add a lot of value in terms of the next stages of the project, in terms of how we would go about deploying these on the network, because we were able to test out more unusual types of configurations that would be difficult to test otherwise. But obviously, we also tested all the prescribed and intended ways of deploying the device, and the Power Networks Demonstration Center independently verified that the inherent algorithm fidelity, algorithm accuracy from these tests has to be within 1% error. There's a few complex issues around interconnection. So in ManWeb, we have a heavily interconnected network, and in central London, there's interconnection as well. And we learned a lot about how we would need to deploy on those sorts of networks as well. So the next step was to then replicate this on a live test network. If we go to the next slide. So to do this, we needed to find a live test network that was had representative fault level of an actual distribution network. It was quite difficult to find because on real distribution networks we can't just throw faults, because what we wanted to do was be able to throw solid air fault and measure the fault current and compare that to the predicted fault level from the real-time fault level monitor. There's a few outdoor test networks in the UK, but they weren't suitable because they're not backed by an actual grid network. So we had to go further afield. We explored a facility in Australia, and we also explored one in Hungary, the Vaki laboratories in Hungary. And the one in Hungary turned out was the best option for us. They've actually got a test network there that's fed from the Hungarian grid, so we've got real representative fault level. And as part of their facilities, they could close a breaker to throw a solid air fault and actually measure the fault current. So just move on to the next slide. I think there might be a photo. There we go. So the real-time fault level monitor was just deployed within that live network facility, connected up exactly as it would be on our distribution network, allowed to run to capture fault level measurements, and then they closed the breaker to create that air fault and measured the fault current. Incidentally, this was all during COVID, so we all had to jump through multiple hoops to get people to actually travel there to keep the project on track, which was a interesting time for everyone, I think. If you just move to the next slide. So this is an example of some of the assessment waveforms that were obtained. So just the disturbance pulses applied, the LV, and the measurement of the voltage response and the computation of the fault level for each one. So you've got the peak fault level traces at the top and the RMS fault level underneath. There's some observations around how noise affects the measurements and the implications in terms of change in network activity. But again, and as we see on some of my slides later from our deployments, we can see fault level as a dynamic value rather than a static value. And just move to the next slide. So I think we've got the comparisons. So so as you can see there, we captured 14 measurements where we directly compared the predicted fault level from the real-time fault level monitor with the fault current that was measured during those tests. And the difference in magnitude between the predicted measurements and the actual measurement for RMS fault level, the 90 millisecond RMS fault level, so the average was around 0.78% with a worst case of 1.61%. Again, we learned an awful lot from this. So there's some things which are impossible to predict. So, for example, if a circuit breaker, if the poles of a circuit breaker don't close at precisely the same time, and they're slightly asynchronous, then that could actually affect the fault current, the end value of the fault current. So it's impossible to get a absolutely perfect comparison, because there's physical limitations in terms of what we can predict in the network. But nevertheless, as you can see, we're extremely pleased with the comparison of results there. We go to the next slide. So this one's back to me. Anyway, so this is now the first example deployment in a real network location. It wasn't the first one we did, but it's quite a good one to illustrate how we go about deploying these on the network. So this is a primary substation location in Glasgow, and at this particular site, the local distribution transformer is in the outdoor compound. The real-time fault level monitor is rated for indoor use only, so it has to be housed indoors. So at this site, we identified space within the protection and control room. We ran a new connection from the LV distribution board of that local transformer, and you can see the route that we ran it around the switchgear building into the protection control room, and we terminated it just behind the real-time fault level monitor there on the wall behind it. And that's where we connected the LV inductors, the LV disturbance generator, as we call it, and we were able to take a connection to the VTs for each of those primary transformers from within that protection and control room as well. So the way our network is configured at this site is we have 3 primary transformers which all feed the same 11 kV bus bar system, and so we've configured a connection from each of those VTs with a changeover facility should we need to change between one and the next. So a little bit of supporting works, but not major, certainly in comparison to what we would have to do for major fault level reinforcement works, for example. So generally speaking, it's relatively straightforward to deploy. I think I'll now hand back to Adam, who could take us through a similar example for UK power networks, an initial view at some data, and then I'll have a bit more of a detailed view at some of the data that we've captured.
Thanks, Ralph. So in the next few slides, I'll share more about the trials that we've done in the southern part or patch of UK power networks. So right after the stage 2 kicked off, we had to one of our earliest priorities was to select the suitable sites where we can practically demonstrate the operation of the RTFLM. And this was not a really straightforward exercise. We had to go through an iteration of shortlisting and site surveying and work around restrictions that allowed us, that meant that we had to scrap or walk away from the sites that were simply chosen in an earlier stage. In this particular example, this is a 132 to 11 kV grid site. It ultimately stood out because it ticked a lot of boxes, mainly the availability of space where we can install the unit, the minimal civil work and connection required, and additionally, most importantly, there's an on-site office which allowed our operations team to monitor the system closely. From a supply perspective, the system was fed via the LV supply was fed to the RTFLM via the auxiliary transformer that you can see in the top left-hand corner, via the LVAC board, The third picture is just the when we had to do some civil work. Basically, the cable was running over a or in front of a stores room, so we had to do not significant civil work, but we had to bury the cable. We installed the cutout to allow us to isolate the system safely if there is any reconfiguration or rewiring required on the RTFLM. And finally, we fed the VT connections from the bus bar. And the last picture on the bottom right-hand corner shows the RTFLM connected. Now, at this stage, it was a very early stage results. So what I'm depicting here in the graph is it's less than a minute actually recording, but bear in mind that this was the very first recording that we captured, but we were already seeing meaningful results. So the data captured on site shows that the RMS fault level current is recorded was 13.2 kiloamps, while the peak was just under 33 kiloamps. The results were calibrated, and it suggested that the RTFLM measured the fault level in 0.5% above the calibration device. So even from the outset, this site gave us confidence that the system could deliver credible, stable measurements, setting the foundation for the wider trials that followed. Can move to the next slide, Ed. This is a very interesting slide that I wanted to also share. Again, this is of the same 132 to 11 kV grid site. The results depicted here were recorded over just about 2 hours. So this is exactly a good example of what we're expecting from an innovation project that is novel and trying to solve a big challenge. We learn as we went through. The graph shows that the RTFLM responded to normal operation actions and closing circuit breakers. I want to stress up front, it's not about the absolute values at the start of this graph, but what matters is the operational insight that we gained and how that informed our unit settings, configuration, and wiring as we went through the project. So under the normal running arrangement, the fault level settled at 13.3 k amps, which was broadly what our operational team expected from the site. And having closed the circuit breaker, the value increased to around 24, and that aligned much more closely with the partial transformer paralleling. And the later trace, there's also an interesting dip towards the later part of the graph. It shows that there's a visible step change that also coincided with the reduction in the embedded generation. So what we've learned from this early stage site that although we didn't have again, as I mentioned earlier, the nature of this innovation project, we had to learn as we go. It demonstrated, the results demonstrated exactly what we needed at that point, that the system responds to real operational change, and we could refine configuration moving forward towards reliable and repeatable behavior. Ed, if we can move to the next slide, please. So this is another site. This is an 11 kV site. What I'm trying to depict in this slide is we've managed to gather data over a lengthy period. I just want to make sure that we're all aware that these were the daily average RMS fault levels. So the RTFLM would measure maximum, minimum, and mean values, and what is plotted in this diagram is the mean values that have been averaged for on a daily basis. As we can see that the RTFLM recorded data that is well below our ADMS system, which is showing some the live data that the operational team would make use of, and it's well below as well the long-term development statement that we publish twice a year. This gave us the confidence that the comparison between the RTFLM and the ADMS directionally consistent and generally responds. So and there was a consistent offset between the data sets. The conclusions that were made from these sets that there's a further deep dive exercise required, and the early justification is points out to the cautious assumptions in the models, whether it's planning or operational, and also the quality of the data that we receive from the transmission side. The graph at the bottom, what I'm trying to show here is it's a zoom in the from the data from the same site, but what these red and green boxes depict is the system was generally corresponding to generation that is happening over time, and the green boxes shows that where both changes in the ADMS and RTFLM, which is the blue line, are closely or almost identically aligned, except for the two cases where in the red boxes. So that gave us further confidence on the system operation, and from there we carried on with the remaining 4 installations on our site. I shall pass back to Ralph now, who will show or present more granular data of what that means. And back to you, Ralph.
Thanks, Adam. I've just got an eye on time, but it's just the last few slides now. So, so at Scottish Power, we've had some devices deployed for a couple of years now, and captured data over from other sites before that. So over the next couple of slides, I've just pulled out some of the more interesting examples. These are a little bit more granular. So on this slide, the data has been averaged over 30 minutes, which is aligned with how we treat data during our system studies as well. And this site is a 6.3 kV primary substation, same ones from the photograph earlier, in a city centre location. So we've got lots and lots of different things connected to our network in city centres. And the interesting thing, as you can see from this trace, is we can see a clear variability between daytime and nighttime in terms of the fault level, and also between weekdays and weekends as well. And in fact, you could even see a slightly longer weekend where there was a bank holiday. So there's obviously some customers connected to the network in that area that are impacting fault level significantly during those times. And about 2/3 of the way across the graph, you could also see that there's a step change in fault level where there was a network switch event. So the network topology changed. That resulted in a step change in the fault level. And then you see the same sort of variability as before until the network was returned to the original topology, and you get that step change again in the other direction. So again, this is really sort of opening doors, and you know, we could see fault level as a dynamic value. So operationally, for example, the control room might decide that if they're worried about fault level and they want to do some switching, if they know from trends that the fault level is lower in nighttime or lower at the weekend, they can potentially schedule the switching for those times instead. If we move to the next slide. So I've just got 3 more examples here that I've pulled out. So what I've tried to pull out here is the really interesting comparison between the system study models, which is all data that we've published in our long-term development statement, and comparing that with the maximum fault level that the real-time fault level monitor has seen over a period of weeks or months in some of the cases. So the substation on the left is a primary substation. It's a relatively new substation, so the fault level is quite consistent. There's not a huge amount connected at that location of the network at the moment. So the board is about half full, and you can see there's a very close correlation between the maximum fault level that's being measured during that period and what the models were telling us to expect. So there's a variance of -1 and +1 for peak and RMS break fault levels. On the right hand, I'll just go to the right hand one first, which is the another primary substation. This is an older substation with a lot more connected to it. Again, we're measuring fault level at 11 kV, and there's measurements there over a period of several months. And the maximum that the fault level monitor measured during that period of time, 30.7 kA, which is 1% higher than the 30.3 kA that the models were telling us to expect. And again, with the RMS break, slightly higher, 3% over that period of time. But when you actually look at the traces, you can see that those peaks are actually very infrequent, and the vast majority of the time the fault level is lower than that. And similarly with the middle one, which is a grid substation site where we're measuring 33 kV fault level, in this case the peak fault level from the models is actually 8% higher than what the fault level monitor saw during that time, and the RMS break within about 1% there. But again, from the trace we can see that there's quite infrequent peaks of fault level, and the majority of the time that the fault level is actually lower. So we're still exploring the best ways to get best value out of the data and what we can do. So for example, we're potentially exploring new control systems using the data to facilitate new connections to maximize the utilization of the network based on our improved understanding from this data of what the fault level activity is. Or by improving visibility of fault level and understanding of it, we can look to defer network reinforcement as well. And just go to the final slide, please, which I'll just quickly wrap up because we've got 5 minutes left. So it's been a very exciting and successful project. And just to reiterate the benefits of why we're looking to do it, why we're looking to deploy real-time fault level monitoring. So firstly, improving the visibility of network fault level. So obtaining fault level at network node based on real-time measurements rather than solely relying on offline models. Obviously, we can then use that to support the system studies. So we can use the measurements we obtained to verify and calibrate network models and help try and remove some of the uncertainties from the necessary assumptions that we use. Where modeling input assumptions are found to be a bit pessimistic in default level calculations, it might be possible to open up a small amount of network capacity and or defer network reinforcement. And in terms of our business case for deploying these in ED2, spend I've calculated over 40 million in customer savings across Rio ED2 by deployment of directly from deploying real-time fault level monitoring and enabling us to defer network reinforcement. And finally, greater confidence in network safety. So by adding real-time fault level monitor measurements to fault level assessments, provides us with additional reassurance that network fault level is being managed within safe limits. And that's it for me. So I think I hand back over to Angus, as we have got a few minutes for questions, but we're happy to follow up with any questions after this session as well.
Thank you very much, guys. Yeah, so Angus is down as the contact here. So this slide pack will come out to you after this over the next few hours. So Angus's contact details is there. So any additional questions that we don't get to cover today, please feel free to contact Angus and he will forward those on to the relevant parties within the project.